Here we go. All right, so here's what the notes look like from last time. And we pretty much covered everything in this section. We just have one last example where the derivative might be a little bit harder to deal with than before. So we talked a lot about what the derivative tells us about the graph. There were a lot of things that we were doing and a lot of things that we were plugging things into and a lot of different ways that we represented our answer. And I just want to do one more example so we have a little bit of practice on doing this since there's a lot of different things that I can ask you on this section. We did intervals of increasing and decreasing using the first derivative test or the second derivative test to find local mins or local maxes. We talked about concavity, which told us if the function was facing up or facing down. We talked about inflection points where we switched from concave down to concave up or the other way around. And we did a lot of different types of questions. So what I'm going to do in this example is just go through this derivative. I'm going to kind of leave it up to you, but we'll do this step by step so we're on the same page throughout. Okay, so example number 7 is the last example in this packet here. And we're looking at the curve y equals x times e to the 2x. Okay, whenever we deal with questions like this, I always like to find both the first and second derivatives first. So why don't I give you a few minutes to do this? And in this section, if you ever finish a question, you can always go to the next one, okay? So I'll leave this step by step, but if you want to go on to the next question, then feel free to go ahead and do. All right, I think some of you are through the derivative part. I kind of want to go through this with you, first of all, because I made a mistake when I did this at home, which makes me sad. It was the first part of the entire question, but also because I kind of want to show how we do product rule and the chain rule at the same time, because I think we might have forgotten that. Okay. First derivative, we said that we're going to use the product rule. And I guess our product rule is where the first function f is x and the second function is g. Before we do the product rule, let's find the derivative of g e to the 2x, and then we can kind of go back, okay? So let's find the derivative of e to the 2x, okay? When we do this, I guess we have to have an inside and an outside. What's the inside function? That's the outside. Yeah, inside's 2x, and then as we said, the outside is e to the something, right? Okay, so using the chain rule, we need to do the derivative of the outside first. What's the derivative of e to the something? E to the something, right? So it's going to be e to the something times the derivative of the inside. What's the derivative of 2x? 2. Good. So we can just stick the inside back in that box. So we know that the derivative of our second function is 2 times e to the 2x. Okay, so that's the derivative of our second function. Okay, now let's do the product rule. It says we have to do the first, which is x, times the derivative of the second, which we said was 2 e to the 2x. And then we're going to add on the second, e to the 2x, times the derivative of the first, which is 1. Okay. Cleaning this up, this is 2x e to the 2x plus e to the 2x. Okay. Once we're here, we can find the second derivative like this. I think I saw Jude do something before he found the second derivative. Do you remember what you did?
I took out e to the 2x from all sides.
Yeah, it looks like we have 2 terms that have e to the 2x. Why don't we just factor that out? And then we'd be left with 2x plus 1. So now we just have 2 factors, and it might make it easier to use the product rule in the second derivative, right? All right, let's find our second derivative. Same thing, let's use the product rule. We already know what the derivative of e to the 2x is. We did it up top. So let's just do product rule again. We need to do the first, e to the 2x, times the derivative of the second, which is 2, plus the second, 2x plus 1, times the derivative of the first, which we said up top was 2e to the 2x. Okay. Cleaning this up, looks like we have 2e to the 2x plus 2x plus 1 times 2e to the 2x. Now that just looks a little bit messy. Why don't we take the 2e to the 2x and move it to both of these? Okay, so let's distribute so it looks a little bit better. Looks like we have 2e to the 2x plus 4e to the, 4x e to the 2x plus 2e to the 2x. Any ideas on how to simplify this a little bit better? Yeah, we could do that, but let's make it, let's just do that. Let's do that. 2e to the 2x, let's take that out. What are we left with on the inside? Yes, so, well, yeah, but let me do it step by step though. So 2e to the 2x divided by that would be 1 plus 2x plus 1, and then that's how you got the 2x plus 2, right? So 2e to the 2x, 2x plus 2. Any other way we can factor this out a little bit better? Take out another 2. So this is really 4e to the 2x times x plus 1, right? Okay. So there's a lot of steps. If you got there without the steps, that's also fine. So we got our first derivative, which is, let me make this a little bit bigger, e to the 2x times 2x plus 1. And then our second derivative is 4e to the 2x times x plus 1. All right. Next up, let's find the critical numbers. How do we find the critical numbers again?
Finding 0 of the second derivative.
Not the second derivative, first derivative, right? So in order to find the critical numbers, take the first derivative, find where it equals to 0 and where it doesn't exist. Okay, so that's what we do for part B. All right, if you're done part B, you can move on. All right, I'm gonna write up this answer mainly because I don't know, I kind of want it to look all neat at the end. I'm not saying that you guys aren't neat, but I like having the handwriting consistent since I already did the first and second derivative. Okay, so I'm gonna take my first derivative, which is e to the 2x times 2x plus 1. I'm gonna set that equal to 0 and see what happens, right? I've got two factors, which means I think I saw everyone do this. E to the 2x, set that equal to 0. Take 2x plus 1 and set that equal to 0. I think I saw everyone solve this and get x equals -1/2, right? So -1/2 is definitely a critical value here. I saw some people take the e to the 2x equals 0 and be like, oh, the answer to that is 0. Is that right? Oh, right. E to the 2 times 0 is actually 1, right? E to the 0 power is 1. So 1 does not equal 0. How would we go about solving this?
Natural log of both sides.
Yeah, right. In order to solve anything within E, normally what we do is we'll take the natural log, which cancels out E. So it's ln of both sides. Okay, so whenever you see an E and you want to cancel it out, take the natural log of both sides. On the left-hand side, we'll be left with 2x. On the right-hand side, we're left with the natural log of 0. Okay, what's the natural log of 0? That doesn't exist, right? The reason it doesn't exist is because if you ever graph the natural log function, it looks like this. There's a vertical asymptote at x equals 0. So 0 is not in the domain natural log. There's no value that I can take e to and get 0. Okay, so this actually gives us no solutions here. Okay, so there's no value where e to the 2x actually equals 0. Okay, so we're kind of at a dead end there. All right, is there any place where the first derivative doesn't exist? At 0, I can try plugging in 0, e to the 2 times 0 times 2 times 0 plus 1. That gives me e to the 0th power, which is 1 times 1,
Oh.
which is 1. Yeah, so that does exist. Are there any places where the derivative doesn't exist? No, right? There's no place where the derivative doesn't exist. E exists for all real numbers. Polynomials exist for all real numbers. So we're actually good. We don't have to check anywhere else. So our only critical number is -1/2. Okay, and remember, critical values are x values. That's where we're going here. All right, let's do part C. Okay, part C asks us to use the second derivative test to find any local mins or maxes. Let's just review what that says. Second derivative test tells us to, well, what does it tell us to do? And what exactly are we like doing? So what numbers are we plugging into what functions? Critical numbers. So I'm going to take the critical numbers. And where am I going to plug them into? Yeah, right. It's the second derivative test, so we probably should plug things into the second derivative, right? So we're going to plug the critical numbers into the second derivative. Okay. Now, just a little review. If the second derivative is positive, what does that tell us? Local min, right? I know it's kind of counterintuitive. If it's negative, then it's max, right? What happens if the second derivative is 0? Yeah, it kind of fails, right? You have to use the first derivative test. So we have like a fail here, okay? And we have to use the first derivative test. So I'm gonna give you like a minute to do this one because I think it's not that bad. All right, I know some of you are still working. Now for the second derivative test, I saw a lot of you setting up a number line, okay? Now, don't set up a number line for the second derivative test. Second derivative test is a lot easier than doing the number line and plugging things in. If you set up a number line, you're actually doing the first derivative test, which is a lot harder than the second one, okay? Second derivative test looks a lot easier. We're just plugging in our critical numbers. Now, our critical number that we found was -1/2, right? Is that the number that we found? Yeah, okay. All you have to do is plug this in to the second derivative. So plug that in to f double prime. Using our notes from part A, our second derivative was, let me just copy this down, e to the 2x times 4x plus 3. So plugging it in gives me e to the 2 times -1/2 times 4 times -1/2 plus 3. Okay, simplifying this, we get e to the -1 times -2 plus 3. And that is 1 times e to the -1. Is that right? Yeah. All right. Once we're here, kind of confusing, right? Is this a positive or negative number? Positive. Why is it positive? Not 1. Saw Maddie raise her hand. Did I plug this into the wrong thing?
Yeah.
I'm using my notes, which gave me the wrong second derivative. Oh gosh. Thank you, Maddie. All right, let's plug this in. This is why I double check my work before I come in here, because I do really dumb things when I try to do examples. So thank you for catching me on that. All right, we're using the 4 e to the 2x times x plus 1. Is that the second derivative? Okay, good. We're on the right page. Thank you so much, because I would have continued on and then it would have been really bad. Okay, so plugging in -1/2, we get 4 times e to the 2 times -1/2 times -1/2 plus 1. Okay. Cleaning this up, we get 4 times e to the -1 times 1/2, which is about 2 e to the -1, I think. Okay. Now, it's kind of confusing looking at this. We want to know if it's positive or negative. We don't really care what the number is. Is this positive or negative?
Positive,
Positive. Why is it positive?
because e is a positive number, it's in the denominator.
Yeah, you were like, okay, I know e to the -1 is literally just flipping it to the denominator, right? So just as if e was a regular number, this is the same thing as saying 2 over e. Now that there's like no negatives in the exponents, and now it's pretty easy to see that this is a positive number, right? Good. So this is a positive number. Okay. Does this mean we have a local min or local max? Counterintuitive. Local min, right? It's the opposite of what you think. Usually when we think of positive, we're like, oh, that's a maximum, right? Opposite for the second derivative test. This is a local min. Okay. Now, would 2 over e be my local min? No, right? So I know it's very tempting to just circle like the number that you ended up with and being like, that's my local min. That's not my local min. That's just the second derivative at my local min. Okay. So how do I figure out what the actual local min is? So how can I say my answer?
Local min at f of negative.
Good. F of -1/2 is my local min. Okay. So you can either show me this on the exam. WebAssign probably won't like this answer because it's not like a number. In order to get my answer, I'm going to have to plug this into the original function. Okay. So plug into original function. Okay. My original function is, oh gosh, x e to the 2x. So I'm going to do -1/2 times e to the 2 times -1/2. And that gives me -1/2 times e to the -1, which is -1 over 2e, I think. No, is that right? I think that's right, right? Okay, good. All right, sometimes I kind of doubt myself in my arithmetic and I get a little scared. But this is my local min. Okay. Any questions on part C? Okay, do we feel a little bit more confident in using the second derivative test? All right. Let's move on to part D then. Now part D is asking us to find the intervals of concave up and concave down. Okay, when we're asked to find the intervals of concave up and concave down, this is when you want to set up your number line. Okay, because we want to find intervals. Number line is when we care about the intervals. Okay, when we're finding these intervals, what are we doing in this question? Like what's the first thing you want to do? Well, what function tells us about concave up and concave down? Second derivative. I want to know when the second derivative is positive or negative. So maybe I need to find those points where we change from negative to positive, which is where the second derivative equals 0. Okay. So what you want to do here is set the second derivative equal to 0, find those points where that happens, and then set up your number line. Okay. When you set up your number line, what function are you plugging things into? Oh, the one that tells us about concavity, which is which function? Second derivative, right? So sticking with the second derivative here. All right. I'm going to do this on the side here because I did this wrong. All right, I know a lot of you are still working on this. I kind of want to go through this real quick. So if you're still working, you can kind of drown me out. But if you want a little hint, I'll show you. Okay. Now, we did find that the second derivative is 4 e to the 2x times x plus 1. So we really want to set that equal to 0, right? Okay. Well, we have different factors. So I can set the 4 e to the 2x equal to 0. And I can also set the x plus 1 equal to 0, right? Okay. Does 4 e to the 2x equal 0 have any solutions? Well, let's find out. We can divide by 4. So e to the 2x equals 0. Is there any place where e to the 2x equals 0? No, right? If you took the ln of both sides, you would find out that your calculator would give you an error. So this is kind of like a dead end. There's no place where this equals 0, so we can kind of just leave it alone. All right, this equation gives us that x equals -1. Okay, so this is something that we want to put on our number line. Okay, with concave up and concave down intervals, we also want to find where the second derivative doesn't exist. Okay, but I did promise you that I wouldn't give you one where the second derivative didn't exist, so you don't have to think about it. But if you use calc a lot in the future, then just keep that in mind. All right, let's set up our number line here. Okay, we definitely want x equals -1 on the number line. Okay. Let's find some values to plug in here. What's an easy number to plug in that's less than -1? Yeah, let's plug in x equal -2. And what function are we plugging this into? The second derivative, right? You can either remember to do this, or you can just think about what we're doing. We're trying to figure out if we're concave up or concave down. The function that tells us about that is the second derivative, right? So we're plugging it into the second derivative here. So we have 4 times e to the 2 times -2, which is -4, times -2 plus 1, which is -1. Okay. Now you can find the number, but is this going to be negative or positive? Negative, right? We have a bunch of positive numbers times a negative number. This is going to be negative. So are we concave up or concave down here? Good, concave down where we're negative, right? All right. What's a good number to plug in that's greater than -1? Yeah, let's plug in x equals 0. So that would be 4 times e to the 0 times 0 plus 1, which is 1. Is this going to be a positive or negative number? Positive, good. So that means, I guess, it's pretty obvious that this one's going to be concave up, right? Okay. So when you're typing this into WebAssign, let me just put our answer up here. Okay, concave up intervals, I'm just gonna say CU. Okay, where do you think? Okay, we already talked about that. We know that it's between -1 up to all the positive numbers. We know that positive infinity gets a parentheses because infinity always gets parentheses. Is -1 a parentheses or bracket? Parentheses, right? We're not including -1 because we're not concave up at -1. We're concave up after -1. Okay, so we get parentheses here. Same thing goes with concave down, except we're going from -infinity to -1 instead. Okay, so when you type your answer into WebAssign, this is how we're writing our answer. All right. Any questions on part D? All right, finally going on to part E. This one asks us about the inflection points of the function. What are inflection points? What does that mean?
It switches between concave up or down.
Good. It's the point in the function where we switch between either concave down to concave up or concave up to concave down. Okay, so look where we switch from either concave up to concave down or concave down to concave up. Well, we can use our chart from part D to do that. Looks like at x equals -1, that does happen, right? We switch from concave down to concave up, okay? So looks like x equals -1 is where an inflection point happens. Is this my inflection point? Or would I accept that on a test, which is really the answer? No, right? Because an inflection point is a point, right? It is an x and y coordinate on a graph, okay? So I need to find the y coordinate. What am I plugging -1 into? The original function. I want to know the point on the function where we switch from concave up to concave down. So I'm going to plug this into my original function, which is f, okay? My original function is, gosh, I kind of forgot what it was. Good. X times e to the power of 2x things. So f of -1 is -1 times e to the -2. Okay. Simplifying this a little bit better, we have a negative exponent. Negative exponents go down, right? So this is -1 over e squared. Okay. So taking a look at this, our inflection point is going to have an x and y coordinate. The x coordinate is going to be -1. The y coordinate is -1 over e squared. Okay, so that is my inflection point. All right, lots of stuff that we did here. Any questions on this example? All right. Now we're not done yet, mainly because I want to pass out the papers so I don't have to carry this big stack of papers tomorrow. But we're actually going to switch gears here if we're good with this. And we're going to talk about something new. So because I feel like passing this out now, we have a new set of guided notes to go over. All right. I know I'm going to come back, but I just don't feel it here. All right. Now, maybe a moment to process what we did here. But we're actually going to completely switch gears from what the graph looks like, all these derivatives, and we're going to talk about something completely new at first, but you'll kind of see how this transitions a little bit later. All right, so we are starting to talk about these things called indeterminate forms, which we'll talk about what they are, and the different types of things that we can have. Okay, and let's just go back into finding limits. Okay, so in this example, we're asked to find the limit as x goes to 1 of this function. And I don't know if you remember, because it was a long time ago, but I told you that whenever you saw a limit, we just plug in the number and see if it works, right? That's the first thing that we do. It's the easiest thing to do. Okay, so let's just plug in. Okay, and looks like we got 1 squared minus 1 over 1 squared minus 1. On top, it looks like we have 0 over 0. Uh-oh, that doesn't work, right? Okay, what I didn't tell you before is 0 over 0 has a name, okay? It's not the answer to the function, but it's actually called an indeterminate form. Indeterminate form. Okay, and we've actually seen 2 of these before. Okay, whenever we've dealt with limits that have fractions in them, we've seen 0 over 0, so we plugged it in, we got that, like this example. We've also seen infinity over infinity. Okay, now those 2 ones are the weird ones where we didn't know what to do. We had to do something else to get the derivative, to get the limit, right? Now, you might be asking, what about 0? Oh no. You might be asking where the rest of the screen is. All right. You might be asking, okay, what happens when you get 0 over infinity? Why is that not an indeterminate form? What happens when you get 0 over infinity in a limit? It's just 0, right? Because 0 divided by any number is 0. Okay, so 0 over infinity is not an indeterminate form. That's not an answer to anything. Okay, now another one that you might see is infinity over 0. What's that limit going to be? Does not exist, or it actually exists. It actually is something, because it's positive infinity over 0. What happens when you divide by something really small?
Goes to infinity.
It also goes to infinity. Okay, so those I probably won't throw at you, but we have seen examples of those before. But the 2 ones that we had to do more stuff with is when we got this guy and this guy, right? Didn't know what the answers are. Does anyone remember what we did to find this limit? We factored, right? We factored the top and the bottom. Okay, so let's just recall what we did here. We factored the top and the bottom. Okay, and I know this is stretching way back into things that we did a long time ago. Okay, so this equaled the limit as x goes to 1. Factoring the top, I think we can factor out an x, right? What would be left if I factored out an x? X minus 1, right? And how do I factor the bottom? Good, x plus 1 times x minus 1. Okay. Once we factor the top, oh, this is the limit as x goes to 1, not 0. Sorry. Okay. Once we did that, the top and the bottom both have an x minus 1, so we can cross those out. And what we're left with is the limit as x goes to 1 of x over x plus 1. Okay. Now we have another limit. It looks a little bit different than what we did. We can try plugging in again, right? So plugging in, looks like we have 1 over 1 plus 1, which is 2. And because that's not an indeterminate form, so it's not 0 over 0 or infinity, this is actually our answer. Okay, so even though when we first plugged it in, we got 0 over 0, the answer is 1/2. Okay, so this is what we did when we found limits that had that look like this. We actually had different types of ways to solve these limits. Let me give you another example of what we did before. Okay. So this limit, we have sine x over x. If you tried plugging in, so we could try plugging in 0, we'd get sine of 0 over 0. What's the sine of 0? 0, good. So this is another indeterminate form, right? Which is not our answer. It just tells us we have to do something else to get the answer. Okay. Well, don't know how to do this one. We can't factor it. Does anyone remember how we found this one? It equals 1, or was it 1?
Yeah.
Yeah, it was 1. I don't know why my brain, I don't know why I wrote down 0, but the answer is definitely 1. Gosh, sorry I doubted you on there. This one equaled 1, and how did we know that? Yeah, it was a theorem. We had to memorize it, right? We just had to know it equaled 1. We had different examples where we had to use this like thing to tell us what to do. Okay, so that one we just had to memorize. Okay, now we had other ways to solve these limits. We had the squeeze theorem, if you remember. We had things with square roots, like we had to rationalize the denominator, and that was kind of crazy. But there are all these different things that we use to solve limits when we had an indeterminate form, and we could just use algebraic techniques to find it. Okay, let's do example 3. Okay, here we have the limit as x goes to 1 of the natural log of x over x minus 1. Remember, when we do a limit, we always plug in first, so let's see what happens. The natural log of 1 over 1 minus 1. What's the natural log of 1? It is log 1, but 0, right? That's, if you type in your calculator, you get 0 over 0. So this is another indeterminate form because it's 0 over 0. Remember, 0 over 0, infinity, 2 indeterminate forms. Well, do we have any tools to do this one? I guess, but then you'd have to like find the limit of like ln of that because you're doing e to the, that would be a little bit hard. Yeah, I can't think of any algebraic tools we could do to solve this, right? We can't factor. We can't use the squeeze theorem. We can't rationalize the denominator. There's no square roots. So we're kind of stuck, right? So we're stuck. Okay, I will tell you the way to do this. There's another tool that I haven't told you about because we didn't have the tools to do it before. And we call it L'Hopital's rule. Okay, so there's another way to solve limits that we don't already know how to do by plugging in. Okay, by the way, I know it looks like L'Hospital's rule. I will actually write that down because I can't spell. Okay, I'm a math teacher. I'm not expected to spell things correctly. But if you see it later in the notes, I call it by accident. I'm very sorry. Okay, what this rule says is, let's say I want to find the limit as x goes to a, right, any number, of f of x over g of x. So all I'm saying is we have a fraction, and I have a function up top and a function on the bottom. Okay. That's all we're talking about when I say f and g in this definition, okay? Let's say f and g are both differentiable, so I can take the derivative of both the top and on the bottom, okay? And g prime is not equal to 0. So if I take the derivative of g, I'm not going to get 0. I'm not going to divide by 0. That'd be a little bit weird, okay? Don't worry about the open interval I. Don't worry about that, okay? Let's suppose that the derivative of the top equals 0 and the derivative of the bottom equals 0. Oh, not the derivative, the limit. Sorry, the limit on the top equals 0 and the limit on the bottom equals 0. What is that telling me about, what is that saying? So what's that line kind of telling me what happens? Well, isn't that saying that I get a 0 over 0? Like if I plug in my numbers, I'm getting a 0 over 0 type limit. That's all this is saying, okay? This line is saying I have a 0 over 0 type indeterminate form. This one is saying the derivative or the limit of the top and the limit of the bottom is both infinity, plus or minus, okay? So what this is telling me, I get a infinity over infinity type limit, okay? So if you either plug in and get 0 over 0 or infinity over infinity, the L'Hopital's rule works, okay? If this happens, then the limit of the function that I'm trying to find is also the limit of the derivative of the top over the derivative of the bottom, okay? Now, before you go, I want to say one more thing. People get confused because it's a derivative of a quotient. We are not doing the quotient rule here, okay? So this is not quotient rule. We are taking the derivative of the top and the derivative of the bottom, which is not what the quotient rule tells us to do, okay? We're just derivative of the top, derivative of the bottom, sticking them on top of each other. All right, we'll come back to this next class. So tomorrow we'll talk a little bit more of how to use this, and I guess I'll see you tomorrow.